All right, so this is lecture 10, and it's Grover iteration. It's a routine that's used for search algorithms. And so this is what we're going to look into today. It's kind of somewhat generalizing the DJ algorithm. I've decided that it's safer to call it DJ than Deutsch Joseph. That way I won't misspell it. So it's kind of pushing this idea along about the DJ algorithm and using some of that, but this has a more precise application. The problem for this quantum search algorithm is that and we've seen this briefly, but let me remind you, you have a function from a set 0 to n minus 1. Here capital N is 2 to the n, and it's because we're going to encode the different elements as binary sequences. And it's going to map to either 0 or 1. And in here, you can apply the function f to see if it's 0 or 1, but a priori, you don't know which elements map to 1 or 0. The only way that you can find out is by actually applying the function and measuring it. So in this case, we're going to have a function that maps to 0 or 1. It has n elements, it's n possible inputs, and m of them are going to map to 1. And in this search algorithm, we actually want to find, actually, I don't want to say this. We want to find the x's, I do want to say this. I want to find the x's in this set, so the x's in this set, that map to 1. So we're searching for this x's. And in here, we can have multiple solutions. So if there's a unique solution, m is equal to 1. If there's multiple solutions, m is greater than 1. So this is the search problem. Questions? So this is the algorithm. And this is what we're going to discuss and go through the different pieces of what's going on here. And in here, the idea is that you're going to input n qubits, which are going to encode the possible inputs. And then you're going to have what they call here an Oracle subspace, an Oracle workspace. And these are ancillary qubits that are needed to apply, in particular, the Oracle function, which is the part of the circuit that actually computes the function f. So somehow we have to encode in the circuit the action of the function. And this is going to be problem dependent. So for different search problems, this Oracle part is going to be different. But the idea is that we wanted to have a precise action. So we're going to start with 0, and we're going to have some ancillary qubits, and then we're going to apply this search algorithm, and then we're going to, at the end, it's going to spit out some state vector, psi. And the psi is the result from the first n qubits, and if we let Sol to be the set of all the solutions to the search problem, then it says that if we measure, the result here is that if we measure the state psi at the end, the probability that it's going to be in a state corresponding to a solution is going to be greater than 1/2. And in here, it's not guaranteed to be exactly 1. You can get it depending on the problem and the number of solutions, the size of the, depending on the size of the, of capital N and the size of capital M, so the size of the input set and the size of the number of solutions, this inequality is going to change. So, and you can get it close to 1, but there's going to be in some cases that it's not going to be that close. But the idea in the case that it's not that close to 1, that it's a little bit further away, is that you keep repeating the measurements. And since it's probability greater than 1/2, then in the long run, if you do multiple measurements, then you'll get a solution eventually. So, so if the probability is 1/2 plus epsilon, and you run the algorithm after k number of times, you should get a solution. So, and it's quickly gonna get you a solution. You might not get it in the first try or the second try, but like in 10 tries you'll get it. Yeah.
So is it, like there could be multiple x's?
Yeah.
Is it the same? It wouldn't be the same x.
No, not the same x. Yeah. You're just getting a solution. You're looking for a solution, not, if you are interested in a unique solution or a precise solution, then you're gonna have to change the problem so that it gives you the one solution you're looking for. But on the other hand, there's also, if you keep repeating the algorithm, it's gonna give you different solutions if there's multiple solutions. It's not gonna spit back the same solution over and over.
So more than half the time it will give you
a solution. Yeah, not a unit. It's not gonna be repeating. Yeah.
Can you exhaust the algorithm so it gives you all solutions?
I think over time, if there's m solutions over time, I think you should. So actually, so this is important. This is a good point, that no solution is going to be more likely than the other. All solutions are going to be uniformly likely to be measured at the end. So in that sense, every solution is equally likely. So if you measure, and this is a probabilistic argument, but if you measure it enough times, you should get a good enough sample about all the solutions. And in particular, you do know, in here we assume that we know the number of solutions. And you do know the number of solutions, so you can just keep repeating it you can keep repeating the algorithm to get the solution, to get all the solutions. And potentially, what you could do is that if you start with m solutions and you start with this oracle circuit, then you run the algorithm, you get a solution, then you can switch the search problem to exclude that previous solution, and you would have to change this oracle, and then it would give you a different solution. So you can do it more that way. The tricky part is changing this oracle part, and that's where it gets a little bit tricky. We'll work on a specific example for on Monday, and in that case, we already know the solutions ahead of time, but it's just to see how it works. So in application, somehow you don't know the solutions ahead of time. Then another comment about this is that we are assuming that we know the number of solutions, but that's not always necessarily the case. And in those cases, there's another quantum algorithm to figure out the number of solutions. So and that's something that we'll discuss later, and that's related to the quantum Fourier transform. And that can give you, I think it's going to give you also with some probability the number of solutions in your search problem. So you can make it more robust, the search algorithm. But this is the initial part where you assume you know the number of solutions. Questions? All right. So The idea here is that the full quantum algorithm is encoded by this diagram on the top. This is the Hadamard gate, and this G gates are going to be given by this routine, by this algorithm. And at the end, we'll see that we have to apply multiple G gates, and the number of G gates that we apply depends on the number of solutions and the number of inputs. So what we'll do first is we're going to figure out the action of this circuit on 0 times this. So what we have is that we start with 0 and then we apply the Hadamard gate, and given that, we're gonna figure out what's the action of the circuit. So I'm gonna break it into pieces. First, I'm gonna look at this, then I'm gonna look at this, and then I'm gonna look at this, and then I'm gonna look at everything together. So we'll start going through the action of the Hadamard of each component. But again, this part here, this is the Grover iteration, G. So let's get started. And we'll start with a simple exercise, and this is from the phase part, changing the phase. This circuit, just for the element, and here they're using the notation that 0 represents 0 if you do the binary expansion 0. And then for this vector, or this basis vector, it just sends it to identity, and all other elements, it flips the sign. And in here, you can write it as an operator this way. You apply the minus identity to flip the signs of all of them. And then for the 0, 0, you flip it back to the original sign by adding 2 of that. So the exercise here is to give a geometric interpretation of this operator. And in general, for this whole algorithm, this Grover iteration, to understand it, we're gonna do it through a geometric interpretation. So this is gonna be the first step to figure out, and this is gonna keep coming up. This is gonna be the first step to understand the geometric interpretation of this Grover iteration. So I'll give you a minute to figure out, in a simple case where n equals 2, you either have 0 or 1, what is the action of this operator, of the phase operator on the element, on a general element alpha beta, where if I plot it, this is going to be alpha, and this is beta. And graphically, I want to know what is the action. What does it look like? So I'll give you a second to work on that. And once we understand this action geometrically, then this is the action that's gonna let us understand the action of the whole Grover thing. So it all depends on this one action understanding this concretely. So turn to your neighbor and compare and see what you get. All right, does anyone want to volunteer and tell me what the action is?
Alpha is 0 minus beta 1, so flip it over the 0 cat axis.
Is that what you mean? Is that what everyone else got? Any disagreement? Yeah. So this operator is going to be reflecting the vector alpha beta over the vector 0. So in here, and you can see that the special action of the vector 0 here, and then the identity. So in here, the action is going to be just a reflection. So this is what is going to keep appearing in this operators for the Grover iteration, reflection of vectors. And we can actually see everything in 2 dimensions. So we're going to start. So this face operator is just changing the face of, it's going to change the face of all the bases except for the 0 basis. And it corresponds to reflecting over the vector 0. Now, I want to look at what happens when I sandwich this face operator with Hadamard gates. And in here, the claim is that if I sandwich it, the action is going to correspond to this operator, where essentially I'm switching this 0 for this psi vector, where psi is a uniform distribution over all the basis vectors. So x here is from 0 to n minus 1. And in here, the remark is that the action of this operator is going to be similar to the action of the face operator that we're going to reflect over the psi vector. So in here, for any element phi, I can write it as a linear combination of psi and a vector that's perpendicular to psi with some coefficients a and b that modulus squared add up to 1. And in here, it's the same computations you did in your notebooks, that the action of this operator is going to send AB to A minus B. So this is going to be flipped over the psi vector. So in here, this is the action of this operator. If we sandwich the face operator by 2 Hadamard gates, we're going to be reflecting about this vector. So this is going to be the only difference, or so I claim. So let's go through the argument of how we obtain this identity between the face operator with the Hadamard gates and this reflection over psi. I guess I don't need this. So this is what we want. This is what we want to prove. And by distributing this Hadamard operators, what is sufficient to show is these 2 identities. One, that this Hadamard times Hadamard is equal to the identity, and this is equal to psi psi. And this one is not going to be very difficult. And in this one, the way that I'm going to look at it is I'm going to look at the action of this psi on any basis vector x, and I'm going to show that that's going to be equal to the action of this guy on the left-hand side on any basis vector x. So I'm going to show that the action of the left and the right is the same on any basis vector, so they have to be the same operators. So that's the way that I'm going to show this identity. And I'll start with the first part.
What's little n?
Little n.
Sufficiently large n?
Little n is this.
Oh,
It's the number of qubits. So little n is the number of qubits, and capital N is the all the input elements, which are made up of binary expansion of the qubits.
thanks.
So we're going to do. We have two remarks. The first is that h squared is equal to ID, and in this case, we recall that h is equal to 1, 1, 1, minus 1. This is our Hadamard gate. So h squared is equal to 1 over 2, 1, 1, 1, minus 1, 1, 1, 1, minus 1. And we have 1/2, 1, 1, 1, 1, 2, 1 minus 1, 0, 0, 2. So we have identity. So this is a straightforward check. And for the case of h tensor n squared, it's just a consequence that in here, this Hadamard gate is acting on each qubit independent of the others. So it's the same thing as just, so it becomes essentially, you can commute the tensor product and the power. So it essentially becomes ID. So in this case, we just have to check it in the 2x2 case, which is straightforward. And then for the, so this settles the first part, that H is ID. And then the second part, we need to figure out, we're going to compute the left and the right hand side. And in here, I'm going to recall this identity that we had from the previous lecture, where we're applying the Hadamard gate to the tensor product of the Hadamard gates to any element x. And it's just going to be a linear combination of all possible configurations. In here, let's see, it's going to be 1, 0 to n minus 1. And they're all going to be equally likely, but the phase is going to depend on the dot product between x and z. And in here, if x corresponds to x1 through xn, the binary expansion, and z is equal to c1 through zn, then x dot z is equal to the dot product x1 c1 plus dot 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 xn zn. So this is a computation from the previous lecture, but I just want to recall it. Let's see, let's continue. So I'm going to start with the right-hand side, and what I wanted to, the right-hand side is going to be the action. Let's go back, actually see what the right-hand side is. I want to compute this action. Psi, psi. So I'm interested in the action of psi, psi, x. So this is what I want to compute, the right-hand side first. So to compute this, I just need to figure out what this dot product is for any x. And maybe I shouldn't be, maybe it's better that I don't use the same notation. So let's assume this. Use different dummy variables. So the question for y'all is what's this equal to? So I'll give you a minute to compute it. And recall that the x's and the z's are orthonormal basis vectors. All right, turn to your neighbor and see what you have.
Is that eliminate right, so is it right, and zero. It was.
Bless you.
Yeah, I made fresh rice. I was eating some, and I watched a funny video, and I was laughing and trying to get out of my throat. So there's that thing burning my throat.
It is composed of Z. So if Z and X are orthogonal bases, we by taking the product between side X, you're going to get.
All right, let's see what we got from someone that hasn't participated in a while.
So there's 1 over square root 2 to the n.
Okay, wait 1 second. Let me. 1 over square root of 2 to the n. Does anyone disagree? Did anyone get something else? All right. And why is that? Why is it?
Z and X are orthonormal to each other. The only time that they would not be zero is when they're the same.
Uh-huh.
Which just should only one of those cases, and thus the sum will only have one of those cases, and just do one of the root 2 to the n.
Yep. Correct. Yep. So by the orthonormality of x and c, this dot product, if you do the x, that's only going to be equal to 1 if x is equal to c, and 0 if x is not equal to c. And it only happens once, so you only get this. Great. And so once we have that, we know that this operator is equal to 1 over square root of 2 to the n and psi. So this is actually 1 over square root of capital N psi. So this is the action of the right-hand side. So, and this is for any x. So it just maps it to this constant state. And then now we want to do the action of the left side, which is equal to this. And in here, we're starting from any basis vector x, and the action of the tensor product of the Hadamard gates is again this dot product, or this linear combination of all the elements with faces depending on the dot product. And actually, this is not psi. So That's not psi. And then I apply this. So I apply this. I'm applying this operator first. Then I apply this, which is equal to this. And then I'm doing, what that means is that I'm applying the 0 on the dot product 0. And that's only going to be equal to 1. It's going to be equal to minus 1, 0 dot z when c is equal to 0, and 0 when c is not equal to 0 due to the orthonormality. And this is equal to 1. So this is going to give me, this dot product is going to give me this. This 1 over square root of 2 to the n, by the same reasons as the other case, essentially, times the 0 vector. And then I apply the tensor product of the Hadamard gate again, which is this action, but now x is equal to 0. So I have minus 1, 0 to the z, meaning that this is equal to 1 for all the cases. And this is equal to, and then I have this square root of 2 to the n. So I get that it's equal to 1 over square root of 2 to the n times psi, which is the same thing that I had here. So we see that it's the same action on every basis vector. So the operators have to be the same. So this proves the claim of, this is our claim that this part of the circuit is equal to this. And the important part about this is that we can interpret this part of the circuit as a reflection over this psi vector. Any questions? All right, so far so good. So now let's look at the oracle circuit. So in here, the action of the oracle circuit is to multiply by -1 if f of x is equal to 1. And this is the similar action that we saw in the DJ algorithm, where if the function was equal to 1, it would multiply times -1, otherwise it would leave it the same. And that was done by adding an ancillary qubit in the bottom. And here in this notation, we're forgetting about the ancillary operator, and just keeping it this way. And I think, I'm not sure if I want to do it off the top of my head, but essentially what we had was that you had something x, y, you had an operator that mapped to x, y, mod 2 summation of f of x, and you said x is equal, or y, and you said y was equal to 0 minus 1 over square root of 2. And then the overall action, if you have y set to that, then the overall action would be equal to -1 to the f of x xy. So you can introduce an ancillary operator to obtain this type of operation. So we have this oracle operator, and we introduce this notation for these two vectors, alpha and beta. These are going to be a uniform linear combination of the elements that are solutions. This is for beta. This is a uniform, the uniform distribution of all the solutions, and this is going to be the uniform distribution of not the solutions. And the question here, we'll do another quick one. It's what is the action on, if we take alpha and beta to be our two vectors, or like the solution, the not solution and solution vectors, and we have a linear combination of these two. What is the action of the oracle operator on this linear combination? And remember, O, so this is for you to do. O of, I'll say Z is equal to 1, is it C or minus C? If C is not in the solution, if C is in the solution. Can anyone tell me just right off the bat what the solution would be? What the action would be, rather? Benjamin?
So we define beta as having everything that's in the solution, so all of those should be made negative. So I
Mhm.
think it'll just be like before, we're just into flipping the second part.
So it's going to be A alpha minus B beta. So again, we just flip the sign of the last one. So, and the picture here is that if this is alpha and beta, and you have a vector like this, then it's going to get flipped over the alpha axis. So again, all these actions are flips, reflections over vectors. And the other remark to keep in mind here is that this psi vector, we can actually write it as a linear combinations of alpha and beta. And in here, it's not too hard to see that if you choose A to be this and B to be this, then then the psi vector is going to be this linear combination. And in particular, we have square root of n minus m n times what's alpha is 1 over square root of nm times x not in the solution, x, I might be off by a factor. And this is m over n, 1 over square root of m. And this is x, and this is x in the solution. So what we have here is that this cancels with this, and this cancels with this, and I'm going to be given 2 over square root of 1 over n. And then this is going to be x, which is psi.
Yeah, because the sums are like summing over different.
Oh, yeah, great. Good. All right. I thought my A's and B's were wrong. So yeah. They're over different sets, so it becomes a summation over everything. So it's not easy to see that psi we can write as a linear combination of A and B. So now we want to put all of this together. We have the oracle operator, and then we have this phase sandwiched with Hadamard's. And we're looking at the geometric picture. So, and maybe I should have had the circuit here, but the first state that we start with, and maybe just go back real quick. So we're going to start with 0, and then we're going to apply Hn, and then we're going to apply G. So going into G, we have, this is bad notation because I've used psi again, but we have psi, which is the linear combination, and then we apply G. So that's going to be our starting point. We're going to have this uniform linear combination, we're going to apply the oracle, and then we're going to apply this. So let's go to the geometric interpretation. So this is going to be our starting point, psi, which is the operation of the Hadamard gates. And we said that we can write as AB, and then plotting it here in this alpha beta axis with coefficients A and B, A and B. And the oracle operator on psi is a flip over this axis. So it's going to flip it this way. So and then the flip is denoted by this right angle. So it's going to flip it to minus B. And then the next thing that we apply is going to be this other flip, flip about the psi vector. And so that means that we're flipping over this psi vector over here. And so we draw the line, and we have our right angle, and we flip it over here. So the result is going to be this vector over here. And if we started here with angle theta over 2, we flip it over here to be angle theta over 2, then the overall angle of this is going to be theta, and when we flip it, this angle has to be theta. So the overall action is moving this vector and rotating it to this vector. And so our result is a rotation. And in here, you should note that what's happening to the psi vector is that it's getting rotated towards the set of solutions. And this is why if we apply G enough times, we're going to get a linear combination of the solutions. A few things to note about this drawing is that due to our choice of alpha and beta, since they're positive, we do start in this quadrant, somewhere in this quadrant. And so this is a faithful representation that we start here, and then we go to this quadrant, and then it's gonna be flipped somewhere to the left. So it is getting closer. It's moving towards the B vector. So in here, if psi is AB, we can write it as cosine theta over 2 and sine theta over 2, where the angle is determined by this condition, where we have the number of inputs, the number of solutions, and we divide by the number of inputs. And the result of applying one Grover iteration is that we're going to go to 3 theta over 2. We're going to go to this angle. So we're rotating towards the B vectors. And it's an exercise to now show that GK, if we apply K times, then the angle is going to be this. And so the name of the game at this point is how much do we rotate the initial, how many times do we apply G to get as close as possible to this axis. And depending on what theta is, since it's going to be some multiple of theta, or half integer multiple of theta, you can only get so close. And in some cases, you can actually get there on the dot, but in other ones, you're just going to get close enough. Yes?
So does this mean, like in this example, if we did it one time, that would actually get us closer if we did it 2 times?
Depending on what theta is. If you...
Yeah, I mean, just going off of what your picture actually is.
Yeah.
So like you need to do a specific amount of times
Yeah.
to get it to the...
Yeah. And the question is, how many times? And it depends on theta. And the thing to note is that theta only depends on N and M, the input size and the number of solutions. It doesn't depend on the structure of F. So it's going to be independent of what the search problem is as long as it's fixed N and M. So this is why it's kind of surprising that it's independent of F. And you just apply, if you know how many solutions you have and the input size, you can just get it there. And another trick is that you can arbitrarily change n to be a different size of input size. You can add more inputs and then change the angle a little bit to kind of change what the angle would be and try to get closer. And this, if there's no other questions, this is going to wrap it up. But in the next lecture, we're going to try to implement this for some simple n's and m's and some simple problems. So I'll send out the group assignments and try to communicate to see that someone's bringing a laptop so that you can code it. All right, that's it. Enjoy the week.